everyone, we're going to use derivatives to find mins and maxes and points of inflection. This is also known as finding the critical points of f and f prime. As a reminder, a critical point is defined as like x equals c is a critical point if and only if, I didn't write that in, f of c is defined, so the function has to exist at that point, and also f prime of c is 0 or is undefined. And so your critical points could be a min, a max, it could be a plateau point, and actually it can be an endpoint as well because of the fact that on an endpoint the derivative doesn't exist. So you have to pay attention to endpoints on functions that have limited domains. Okay, so if we're going to find the mins and maxes, points of inflection, basically we're saying give me everything necessary about this cubic function. So our first step is we're going to find our first and second derivative. So f prime of x, we get negative 3x squared plus 18x minus 15. And then I'm going to skip a couple of lines because I'm going to be using some space. So f double prime is negative 6x plus 18. In order to find where the first derivative equals 0, you can use the quadratic equation, or you can factor this guy, which is what I'm going to do, because I find the quadratic equation annoying. So if I pull a negative 3 out, I have x squared minus 6x plus 5. And then I can factor that quadratic and get x minus 1 and x minus 5. So here's our very usable version of our first derivative as a factored quadratic. And then we have our second one. Second step is going to be to find where our first derivative is 0. And that also could be where the first derivative is undefined. In this case, obviously, we have a cubic function. It's a nice smooth curve, and it's defined for all values of x. A function that has a divide by 0 in it, for example, would be where those undefineds might happen. So looking at this factored form, f prime of x equals 0 if x equals 1 or if x equals 5. The next question is, are these mins or maxes or neither? And that can happen as well. So our next thing is we will use the second derivative. Forgot the word derivative. Use the second derivative to ascertain if you have a min or a max. And we do that with what's called the second derivative test. I'm going to just grab this. So if you have a first derivative that's 0, so it's flat, and if your second derivative is negative, a second derivative being negative would be concave down, so it would look something like this. So x equals c would be a maximum. If you have a positive second derivative, it's going to be concave up. So if it's concave up and flat, you have a minimum. And then if you have both the first and the second derivative equaling 0, a couple things can happen. But what we say here is that the second derivative test fails, and we'll talk about this more in the next video. So back to here. If we look at f double prime when x is 1, so f double prime of 1 is negative 6 times 1 plus 18. I'm not even concerned about actually finding the answer. All I care about is the fact that, oh, that's positive. So if it's positive, that means I am concave up. And I like to draw myself a little arc of like, that's what concave up looks like. Because if I draw that little picture, it tells me, oh, I have a minimum. By the way, these 3 little dots in math mean therefore. It's much easier to write than the word therefore. Looking at the second derivative at 5, we have negative 6 times 5 plus 18, which is a negative, so less than 0. So therefore, it is concave down. Therefore, we have looking at that, we can look at it and go, yeah, that looks like a maximum. So here are the critical points of f of x. X equals 1 and x equals 5. We used our second derivative to figure out that at x equals 1 we have a minimum and x equals 5 we have a maximum. And obviously, if you have some of your function being concave up and some of it being concave down, you have to switch in between. So we're going to be looking for our point of inflection, and that is going to be where our second derivative is 0. So we're going to find the second derivative equals 0, which will tell us maybe if we had that a point of inflection. The reason I say maybe is that we have to have a sign change. So basically, does f double prime change signs? And this could happen if our second derivative is 0 or undefined. So looking at our second derivative, this f double prime being negative 6x plus 18, f double prime of 3 equals 0. And it's a linear function, so I know it changes between positive and negative. So x equals 3 is a point of inflection for f of x. Now, this is something, a careful detail. X equals 3 is a critical point of f prime, because that's where f prime equals 0. It's where the derivative of f prime is 0. But x equals 3 is not considered a critical point of f, because a critical point of f, remember, is only where f prime is 0 or undefined. So as a note, x equals 3 is a critical point of f prime of x. It is not a critical point of f of x. So that's something we have to really watch for. It gets a little confusing, and this will get better as you work with it. So the things to keep in mind are the definition of critical point and also our second derivative test. So watch the next video to see what happens when the second derivative test fails.